In the last lecture, we saw how the more or less permanent wind systems in the atmosphere created large gyres in the oceans, in all the oceans. And we also saw how the radiant energy from the sun created a circulation which we call the thermohaline circulation, which was like an immense heat engine. Now, these circulations change, of course, as the wind patterns change. The time scale of the wind-driven circulation is about 2 to 3 years for a particle of water to circulate, say, in the North Atlantic gyre. And during this time, the wind systems can change. And I thought today we would focus our attention on three of this type of change, which, of course, are of considerable importance to the fisheries, and there are also effects on agriculture. So let us look first of all and refresh our memory of the ocean currents, the wind-driven ocean currents. And if we remember, the winds create large gyres, one in the North Atlantic rotating counterclockwise, rotating clockwise, the other in the South Atlantic rotating counterclockwise, one in the Indian Ocean, one in the North Pacific. And these are created by the prevailing westerly winds and the trade winds. In addition to these, there is another current which we didn't mention, and that is a countercurrent runs along the equator directed from the west towards the east. Now, the three areas we're going to focus our attention on for the first part of this lecture are the Indian Ocean. And we're going to look at the Indian Ocean because the monsoon systems of winds which operate over the Indian Ocean change. They, in fact, reverse from winter to summer. And this changes the circulation in the northern part of the Indian Ocean quite considerably. The second area we're going to focus on is the area off South America, off Peru, where the large anchovy fishery of the world is, and there we will see a phenomena called upwelling, which brings nutrients to the surface. And the third area we're going to focus on will be the Gulf Stream as it comes past Nova Scotia. To begin with, let's look at the Gulf Stream. Now, this is a western boundary current. It is, in fact, fairly narrow. It is about 40 miles wide, roughly, and it has been described as flowing through the ocean like a river. And it is rather spectacular for people who have crossed the Gulf Stream. You can see the change in the color of the water, and the navigators are aware that the ship has reached this major current. Now, this the current does some peculiar things after it leaves the continent near Cape Hatteras. It meanders. It meanders very much like a river going through a flat plain. You've probably seen pictures of these taken in an aerial photograph, and the river meanders in great loops on its way to the sea. And the Gulf Stream does in fact do just that, except it is meandering in the ocean. Now, because it's in the ocean, these meanders are not constant in position. They're continually shifting. And we have a pattern of the Gulf Stream meandering across the ocean from Nova Scotia towards the Grand Banks. The Gulf Stream, of course, also forms a boundary between the warm waters of the Sargasso Sea and the cold waters further to the north. And a very peculiar thing was noticed in the 1950s in the Gulf Stream, which we have illustrated in this diagram. Here we have the Gulf Stream, and what I've indicated is the cooler waters to the north in the blue and the warmer waters to the south in the gray. Now, in 1950, during an expedition to track the Gulf Stream, it was noticed that the Gulf Stream had meandered in this fashion and had formed a great loop to the south, and then returned on its course and proceeded to the east. It was also noticed that there seemed to be an eddy rotating which wasn't connected with the stream at all. A little later on, it was noticed that in fact this big loop to the south, which would be over 100 miles long, had in fact broken off, and there had been another eddy formed. They found the remnants of the first eddy, and so that this whole process took 7 to 8 days, so that over a period of a week or two we have this great loop formed, and then we have this eddy broken off. Now this took a lot of ship time, and there weren't too many ships in those days, and to chart this effect. But it has been observed through recent years, and in the last few years there has been a lot of emphasis placed on trying to find out just exactly what does happen to the Gulf Stream. And this of course has become more possible because there have been more oceanographic ships built, there are more oceanographers, and therefore we can spend more time looking at the oceans. And these things can also be seen in the satellites. What has been found, in fact, is that these eddies, which are about 60 miles long, they're various sizes, in fact exist in the interior of the ocean in the Sargasso Sea area for 3 to 6 months. And oceanographers have been very puzzled as to the dynamics of how they are formed, and are still working on this system. And this has raised several questions as to what role do these eddies play in the dynamics of the ocean. Do they in fact take energy from the Gulf Stream, which is originally given to it from the winds? Do they in fact add energy to the Gulf Stream if they coalesce with the Gulf Stream, as some of them have been observed to do? They are of importance in part to the biological life in the ocean. There are different flora and fauna in the cold waters to the north, and when one of these eddies breaks off, it takes with it its flora and fauna. And the eddies are long-lived, 3 to 6 months, and there is time for new flora and fauna to be born, and it's of course of great interest to the biologists. It is generally believed that this phenomena of the Gulf Stream meandering and these eddies breaking off is caused by the bottom topography of the Atlantic, but the theoreticians are still working on this part of the problem. Now let's turn to the Indian Ocean and look what happens there. In the Indian Ocean, we have the monsoon system operating, and in the northern summer, the continental Asia over India warms up with respect to the sea, and over the land the air becomes lighter and we have a low pressure. So the wind systems in the summer are directed to the northeast. They're called the southwest monsoons because they come from the southwest. And so in the summer the prevailing wind system is from the ocean onto the land. And it acts long enough to completely change the circulation of the Indian Ocean to what it was in winter. So in the Indian Ocean, in the summertime, we find a circulation which looks the way I have indicated in the diagram. The predominant currents are to the east. There is a flow out of the Red Sea and a clockwise flow to the east of India. The net result of the monsoons, of course, is that the crops in India are very dependent on the monsoons, because since it's an onshore wind, it carries rain with it, and we have the monsoon rains. Now in the wintertime, the opposite occurs. The sea, because it has such a tremendous heat capacity compared to the ocean, the upper 3 meters of sea have the heat capacity of the whole of the atmosphere. Does not change temperature as quickly as the atmosphere, so we have a cooling down of the land And as the air is cooled, of course, it becomes denser. And then we have the winds blowing from the land onto the ocean, and then we find that this whole monsoon system of currents changes. And what then happens is that the circulation reverses. The predominant currents are from the east, and we have a circulation system such as I've indicated. In the equatorial regions, of course, the circulation is still directed towards the west, and the water is forced into the Red Sea. Now this is really a very large area, and we see a large part of the ocean responding to major changes in the wind systems. Now there are other areas where changes not as large as this occur, but certainly the changes in the wind systems do have an effect on the ocean waters. The third phenomena, which we're going to talk about, is called upwelling, and it is caused again by the Coriolis force and the effect of the Ekman layer. In this diagram, what I've indicated is the land, and this is an artist's diagram of the beach, and a wind which is blowing away from you in this direction. Now, if this was in the southern hemisphere, there would be a mass transport of the surface waters to the left due to the Coriolis force. And this, in fact, occurs off the coast of Peru, where the predominant wind systems are channeled up the coast due to the Andes Mountains, and are quite strong. And so we have the surface waters are forced off the coast out to sea. Now this water has to be replaced from somewhere, and of course it can't be replaced from the land. And the result of this is that there is an upwelling of the deeper waters from 200 to 300 meters into the surface waters, and we have a circulation such as we have indicated in the diagram of an upwelling of the deeper waters, and then the winds drive the waters off the coast. And this occurs in Peru. Now, the importance of it to fisheries is that the deep waters are rich in nutrients, in phosphates and in nitrates, so that as the water upwells, it brings with us phosphates and nitrates, and of course these nourish the fisheries. And off the coast of Peru we have this very large anchovy fishery. There are other areas in the world, of course, where this occurs. There is a big upwelling area off Africa, off the west coast of Africa, again associated with it a large fishery off Senegal. There is also another upwelling area off the coast of California. And not only is the water full of nutrients, of course, the upwelling water is colder than the surface waters, and as a result, in areas particularly off the California coast where this occurs, we get sea fogs formed. Now, changes, of course, in this upwelling system can be rather disastrous to the fisheries, and Peru is an area where, in fact, these changes do occur. And the phenomena has been called El Nino. It's the child. The El Nino means the child, and it's called the El Nino because it occurs just after Christmas and is associated with the Christ child. Now, the situation off Peru is that we have a northerly flowing current called the Peru current, or the Humboldt current, and that's cold because it's coming from the south. And in the just after Christmas, we have the equatorial current, which is flowing to the east, tends to bend down a little bit towards Peru, and this is the normal sort of situation. However, every so often, approximately every 7 years, this whole system changes, and it changes very markedly. What is found is that the countercurrent, the equatorial countercurrent, will push right down the coast of Peru. The wind system breaks down, so there's no upwelling. And the influx of these warm waters down the coast of Peru in place of the upwelled nutrients in the upwelling area just causes tremendous destruction and death in the fisheries. Not only does it cause the fisheries to collapse, but it causes problems with the fertilizer industry. The seabirds, since they are deprived of their seafood, the ones which feed on the fish, die, and their droppings, called guano, is no longer available, so the fertilizer industry collapses. And also, due to the changes in the wind, this warm water, there is tremendous torrential downpours in Peru and the surrounding areas, and there are very large floods. So these are three of the types of thing which happen when the wind system changes. In the situation in Peru, it's so economically disastrous, and it can also have repercussions worldwide because the anchovy fishery is very big and the fish meal industry collapses, that there is in fact at the present time an international expedition into the area to try and find out why the phenomena happens, how it relates to the wind systems of the Pacific, and what is happening in the rest of the equatorial current to cause this to happen. Now, so far we've dealt with the oceans, but we should also pay some attention to what happens along the shore of an ocean. The shore of an ocean is a very complicated thing, of course, and we couldn't possibly describe everything, but I thought maybe what we would talk about is a circulation which is called an estuarine circulation. Now, estuaries are inlets. There are various types, and they occur at the mouth of a river, particularly if the mouth of the river is one which has subsided in geological time. And then we have an inlet with salt water at the bottom of the inlet, and flowing out over the top of it we have fresh water from the river. And this creates a peculiar type of circulation. So let us look at an inlet, a schematic cross-section of an inlet, to see what might happen. Here we have the land sloping away from the mouth of the river towards the mouth of the inlet. On top of it we would have fresh water running out over salt water. And if there's no such thing as friction or turbulence, it would just run out over the top of it. And if we looked at a section through three places, 1, 2, 3, we would find that, for instance, we would have fresh water at the surface, and then it would suddenly become salty very abruptly, and we would have salt water for the rest of the depth of the inlet. The velocity, if we plotted the velocity against depth, we would find that that would gradually decrease if the estuary widens, say, and at position 1 we may have a fairly high velocity dropping to 0 in the salty part. At position 2 we would have a slightly less velocity. At position 3 near the mouth less still as the estuary broadened. Now in fact there are frictional effects between the salt water and the fresh water, and these create quite a different situation. Here we have a diagram, again, which shows our estuary with the land dropping away. But now we have friction and turbulence at the boundary between the salt water and the fresh water. The result of this is that salty water is drawn up into the fresh outflow and is carried along with it. So this causes two things to happen. First of all, it creates an inflow of salt water into the estuary, whereas before we had none. Secondly, if conditions are right, it can actually cause an increase in the volume of flow in the surface waters. So if we looked at this type of estuary, and plotted, say, salt against depth, we would find that at position 1, the salt would it be fresh to a certain depth, and then we would increase and it would be salty, but the increase is not so abrupt. At position 2, further out in the estuary, the freshwater layer has got less, and so we'd have fresh water, and then at less depth it would change to salty. If we plotted velocity, we would find at position 1 we had a velocity in the surface layers which gradually decreased to 0 in the bottom layer. And at position 2 in the estuary proper, as we went through the boundary between the fresh water and the salt, we would find that the velocity in fact reversed, indicating a flow of salt water in. Now this effect can be fairly large. The outward flow in the upper layer can in fact be increased by 10 to 20 to 30 times. And this is what is called an estuarine circulation. And of course it is of great interest to the biologists who are working in coastal waters. The next type of estuary is the fjord, and I'm sure you've all heard of fjords. And the fjord is formed geologically due to a drowned river valley, but with a silt at the surface. Very often the fjord's been scooped out by glaciers and the land has subsided. So if we look at a fjord in cross-section, we would find that there is a very deep basin, often as deep as 600 meters. Then, as we approach the sea, it would rise to a sill, and we would drop off to the open ocean. Now, there are major fjord systems in the world. There's one in British Columbia, there's one in Norway, the Norwegian fjords, and we also have a major fjord system in Peru. The characteristics of these fjords differ. It depends whether there is icebergs, or not icebergs, ice from glaciers providing the fresh water, how deep their sill is. They still exhibit basically this estuarine type circulation. And what we have is again the inflow of salt water into the fjord to fill the bottom basin, an outflow of fresh water at the surface, and an entrainment of salt water by the outflowing fresh water. So in this particular example I've chosen, if we look vertically at positions 1 and 2, we would find very little salt at the surface. It would increase to whatever the salinity of the water was at depth. And associated with it, there would be a decrease in velocity as we move to the lower layer and a reversal. The same at position 2. At position 2, of course, as we approach the open ocean, the fjord become more salty. Now, since these fjords can be fairly deep, several hundred meters deep, the bottom water can, in fact, become stagnant. The biological life of the ocean extracts oxygen in its normal life cycle. And of course, in the open ocean, with the waters moving around everywhere, the oxygen is replenished. Although, in fact, at certain depths there are layers of depleted oxygen, generally oxygen is available. But in a fjord, and unless there is an influx of salt water which is heavy enough to sink to the bottom, the bottom waters will gradually lose oxygen and, in fact, become stagnant. Now, the other thing which occurs is that not only is salt water mixed up, but there's a little bit of fresh water mixed down. So as time goes on, the salty water in the bottom becomes a little fresher, and because it becomes a little fresher, it becomes a little lighter. And every so often, there is an influx of water from the outside, which flows over the sill, cascades into the bottom of the fjord, and we have a renewal of the bottom waters. This may in fact take several years to occur. One place where records have been kept for a reasonable length of time is in Norway at a fjord called Fjord. And here we have a little graph which shows the change in the oxygen in the bottom waters at 400 meters from 1930 through to 1950. Now, here we have oxygen. This is 40%, 50%, 60%, 70%, 80%, 90% concentration of dissolved oxygen. And this time scale is from 1930 to 1950. And as you can see, in about 1931, the water must have been reasonably fresh. Then nothing happened in the bottom of the fjord. The estuarine outflow operated in the upper part, and the oxygen gradually decreased for a period of almost 10 years until there was not very much oxygen left in around 1940. Then all of a sudden, the conditions were such that there was a massive inflow of heavy and water from the outside, rich in oxygen, and suddenly the oxygen shot up to almost full concentration. Then it sort of digged around for a while, and then it gradually dropped off again through to about 1950, and then it suddenly shot up again. And this type of thing happens in other fjords besides this particular one I have chosen. Now, the estuarine circulation is, of course, generated because of the difference in salt between the outflowing river waters and the inflowing salt waters. Not only is this the only factor, what must be considered in these inlets and estuaries is tides, and they can in fact force the whole salt wedge, which we showed there, up the river and down out of the river. The tides also create considerable currents in the estuary, and we find we have sedimentation problems in estuaries. The estuarine circulation itself can in fact build bars at the mouth of estuaries, and they're generally of interest to the biologists. Now, in the next talk, we're going to talk about these tides and waves and their effects on the shoreline.